Thank you very much. I'm honored to be here. Sorry for the cheesy title. But this is the work with Emily Clater, Chiara Damiolini, Daoji, who's here, and Shira, who's also here. Sorry?
Maybe Rohini.
And then I'll mention where the kind of objects that we were looking at comes from. So there are a series of papers of these 4 plus one more person, Rohini plus. And there they study some sort of a moduli space, which I think you see at least some glimpse of, but I mean, you already saw a glimpse of in Melody's lecture today. They were studying some moduli space of pointed rational curves with some sort of a cyclic action, let's say Z mod n action. And I'm sorry to say we will not, or at least in this talk, I will not talk almost anything about that. But the kind of statements that I'll tell you in a short bit is a nice interaction between 3 related areas. So one is this perspective of moduli space of pointed curves that these authors studied. And the other input is tropical intersection theory. And this tropical geometry you can actually find in the certainly there are much close relation between the two. The one that you'll see this week and one more featured, or I'll at least hint at today. And the third input is convexity / log-concavity, which you'll see much of in the rest of Josephine's lecture series. So let me start with the statement, the main statement. And the statement itself is completely combinatorial. There's really no geometry. So let me tell you what the setup is. Let's say I have a finite set E, and we have a partition into, let's say, D many parts. And to avoid trivialities, let's assume 20 parts. Okay. So it's like an international meeting, and there are D countries, and they send, country 1 sends their delegates, country 2 sends their delegates, and so forth. No dual citizens. Actually partition. So I'll think of these as like delegates. D countries. Some flavor text if you like. Now, let's say a subset S of E is a committee if S intersect E sub A. This is at most 1 for every. In other words, it's a group of people in this meeting where every country is represented at most once. Okay? Not necessarily exactly once, but at most once. Okay. Is there a fair way to make various committees? I don't know, but let's just call it that. And let's say I have some n tuple of them. So I have n many committees. Let's fix. So fix S1, Sn, and comes. And lastly, I need one more terminology, which is that of a panel. So again, a subset of E is a panel if every country is represented exactly once. Okay. So it's like a sort of a maximal committee. Or yeah, so it is a maximal committee. Let's call it a panel. And lastly, what do we want to count given this terminology and data? So the data given is a partition. Oh, thank you. Thank you. And we fix this data. And what do we want to count now? Now, given a non-negative vector, integer vector, one for each country. Oh, sorry, one for each community. Such that the sum of the coordinates is the number of countries, D. We'll keep that throughout. Define the following quantity, denoted as C sub alpha. I mean, really it depends on the choices of S1 through Sn, given the partition, but I'll just suppress all those data and just call it C of alpha, depending on alpha. This is cardinality of the following finite set. I'll write it first and say what it is in English. So we want to count the number of panels with the property such that there exists a map, let's say B, T, the indices 1 through n, indexing the committees, such that the fiber of I for every I 1 through n is contained in Si, and its size is okay. So in English, what is this? So I have a bunch of committees where the country is represented at most once. Alpha tells you some non-negative integer for each committee. Okay. And so for the first committee, I get to choose alpha one many people from that committee. For the second committee, I get to choose alpha too many from S2, and so forth. And I'm going to try to make a panel in that way. So I get to choose alpha one many from S1, alpha two many from S2, and I try to create panels. And this count is the count of how many panels I can make. Okay. So that's the definition. Let's see if we are all on the same page. So here's one example. So in this example, D equals 3. So we have 3 countries, or 3 colors, if you like, and 3 committees. So both D and N are equal to 3. So alpha, I've drawn in a dilated simplex all possibilities for alphas whose coordinate sum equals 3. So 3, 0, 3, 0, and 1, 2, 0, and so forth. And on the corresponding diagram, I wrote down what these C sub alphas are. And let me do one example, also as a kind of caution. Let's look at this number, this alpha. So the alpha says 1, 2, 0. So I'm trying to create a panel by picking 1 person from here and 2 people from here. For instance, I can do 1A and then 2B, 3B. Now I could also do 3B, 1A, 2B. But this thing says 1. And the reason is that we're not counting how many ways you can make such panels, but just number of panels that can be created by picking as such. So in this case, both panels I can make 1A, 2B, 3B. So 1A, 2B, 3B by picking this and these two. Or I can pick 3B, 1A, 2B, but that's the same panel. So you just have one. So that's sort of the weird feature of this combinatorial count that, for instance, makes whatever kind of inductive argument you might want to do to say something about these numbers rather difficult. It's not that you're counting the number of ways to create these panels, but counting how many are just possible. Okay, so those are the numbers. And let me say what the theorem is now. So one more notation for a non-negative integer vector alpha. It's just notation. X alpha over alpha factorial. This is just notation for x1 to alpha 1 dot 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 xn alpha n over alpha 1 factorial dot 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 alpha. Here's the theorem. And one, or let me write the theorem first. The statement is, let's collect all these in an exponential generating function using this. In other words, sum over all alphas whose coordinate sum equals d, or all non-negative alphas whose coordinate sum equals d, and c sub alpha, x to the alpha factorial. So this is some polynomial, and the statement is that this is Lorentzian, which technically you don't know what it means yet, but you will very soon, I think like almost first thing tomorrow. So we have this notion of stability, which had a nice implication. And Lorentzian is some generalization of the notion of stability. And the statement is that this polynomial is actually quite nice. It's Lorentzian. Now, we don't know what that exactly means yet, but let me point out some features that you can tell or deduce from the fact that it's Lorentzian. So in this diagram, read in any of these kind of blind directions. So let's read in this way and look at the numbers. I read 1, 2, 2, 1. So first thing you notice is that it has no internal zeros. So it won't read something like 1, 1, and then 0, and then 1. Like no internal zero. Also, it's unimodal in the sense that it keeps going up and then monotonically goes down after some. You read an interaction. And in fact, it's log-concave. In other words, at every point, you're reading these numbers in whatever direction. If I square a term that is bigger than the other two multiplied. So 2 squared bigger than 2 times 1 and so forth. As far as I know, I don't know how to prove such things without going through the Lorentzian technology. Okay. The no internal zero you can actually prove without going through the full machinery that we developed. It's actually a pretty nice application of Hall's marriage theorem, or it kind of boils down to that. Log-concavity, much harder, or at least I don't know how to do it in a more elementary combinatorial way. Okay. And one unfortunate thing about our paper is that this statement appears nowhere in our paper. Unfortunately. It is like 2 to 3 lines like corollary, but by the time I realized this is a kind of neat way of framing at least one consequence of what we did, the paper was already published. So I'm not complaining that it was published. It was like very quick and easy process, but it's unfortunate situation where this doesn't appear anywhere in the literature right now, at least explicitly. Okay. Okay, so that's the statement, and for the rest of the time, I'll tell you as much as I can about what kind of tropical flavored things / log concavity, convexity, and kind of algebra with geometric ideas go into proving this. Any questions so far? Okay.
You have a question, I think.
Oh, yes.
Sorry. I'm confused on the function phi, because phi, it's going from t to like the set of n, and t is just a subset of e.
Yes.
Right? Is e like, what are the elements in E sets? Because then we took the, I'm forgetting the term, I'm blanking on what it's called, but like we have the like the number of things in it. Cardinality. Yeah. We're taking the cardinality of the. Maybe I missed something.
Oh, are you?
Yeah. I want to know what like.
So what I'm trying to say, at least in English, is so I want to make some sort of panel. In other words, a group of people where every country appears exactly once. And this function is saying, okay, I have like, say, T1, T2, T D. T1, if it maps to say like 3, it means it came from community 3.
Okay.
T2, let's say it also maps to 3, then it also came from community 3, and so forth.
Yeah.
And I want it such that the number of times, for instance, 3 is hit is exactly equal to alpha 3, and so forth.
Oh, okay. I see. Okay, that makes sense.
So alpha tells you how many I pick from S1, S2, Sn.
Okay.
And I'm seeing which panels can be created in that process.
Okay, that makes sense. Thank you.
Yeah.
Is the number 1 important? Like, what if I want to allow more than 1 to be drawn from EI?
You can probably do something, but at least I don't have a theorem. Yeah. Or I don't know how to prove if there is such a theorem. Yeah. But it's certainly a natural direction one can take this. And I mean, there are a bunch of games you can play. I mean, why does it even have to be 1 for every j, right? You can have like Cj, where Cj varies for each j, right? So you can really kind of play a different kind of game in various different situations. And in our case, this special case is when we have the most kind of amount of understanding at the moment.
So, when we're counting the C alphas, we just want to know the number, not the number of ways to get it, or what do you call it? Count?
Sorry. You call it however you like. Yeah.
Same thing. But you can play the same game if you wanted to count the number of ways with your beautiful triangle that you have over here. Like, what goes wrong? What's the struggle? Or have you thought about that? Like allowing to count?
So if I want to actually, so for instance, if I want this to say 2, because there's actually like 2 ways to create it, then if I remember correctly, this kind of statement is somewhat easy consequence of kind of known statements about Lorentzian polynomials. But this version just makes it
Stronger.
somewhat harder to analyze and somewhat surprising. Yeah. Okay. So how does one prove something like this? So let me state a rather general geometric statement first. So let's begin with some projective variety. some algebraic variety in a projective space carved out by some homogeneous equations. Strictly speaking, by variety, I always mean irreducible and reduced. So we have some projective variety, let's say of dimension D. And let's say I have various morphisms from the projective variety. Let's say, let's name it F. F sub J from X to some projective space, P, let's say MJ, or some positive integers MJ. So that's the setup. And what do we want to count? For some non-negative vector and let's say I have n many such. So J, once again, let's say I have n such maps. So let's consider an n tuple of vectors such that their coordinate sum equals D. We're going to define some quantity. So first, this is not grammatically correct. First, pick alpha j, any general hyperplanes. Let's say h j1 dot h j alpha j. So for each j, I pick alpha j many general hyperplanes in the projective space. So some general linear function. That's what we have chosen. And then the thing we want to count is the following, which I'll denote C tilde of alpha. And this is the cardinality of the following intersection. So you intersect P1 inverse of H1, 1, intersect dot dot P1 inverse of H1 alpha 1. And you do this for all the J's. Have, I guess, n inverse of H1 dot dot n. And for some of the alphas, it might be 0, in which case you don't pick any general hyperplane, so it doesn't appear in the intersection. And let's do a quick sanity check. So picking these general hyperplanes, and I'm looking at the inverse image of this. So hyperplanes are carved out by one linear equation, and I pulled it back. So all of these inverse images are codimension 1 in X. And in fact, if you believe in Bertini's theorem, they will in fact be smooth.
Wait, what is Bertini's theorem?
Bertini's theorem, at least in characteristic 0, states that when I have a map from a projective right to a projective space, the inverse image of a general hyperplane will actually be smooth. Okay, so I have a bunch of these inverse images of the hyperplanes or hypersurfaces in X. Intersect a bunch of them. I have this giant intersection. And how many do I have? I have D many. The sum of these alphas. So I've intersected D many, the dimension many hypersurfaces, so that should be points. And again, if you keep applying Bertini's theorem, it tells you that these will actually be distinct points, like distinct smooth points. So it makes sense to say just count. So that's what we want, or that's what I'm denoting as C tilde sub alpha. And the theorem, due to Peter Benton and June, is that if I look at the exponential generating function for these counts, given this data, in other words, a projective variety of dimension d, and n tuple of maps to projective spaces of possibly various dimensions, this polynomial is Lorentzian. That's very nice properties. Okay. So at this point, at least the way it's presented, what do we need to do? Well, one way to prove that theorem will be to find the right x and the right maps. Then I win. Modulo the fact that once I find the right maps and x, I need to prove that this kind of intersection count is this kind of counting panels count. Okay. Such things are more easily said than done. And a good deal of that goes through these tropical and convexity ideas. So let me tell you where one can find such x in these maps. And we'll work towards some tropical ideas, and I'll give you as much as time allows on what kind of techniques go into. Things clear here so far? Any questions? Okay. So let's try to look for this x. And there's no kind of definite process on how to do this. And frankly, if I were to be honest, and we were studying this space, which is going to be the x. And then we did some interesting computations with intersection numbers and whatnot. And then found that those actually count those kind of interesting panel counting numbers. So really the development, if I'm to be honest, happened backwards. And often given the combinatorial problem, there's no like kind of step process on how to find x and these maps, if there is any. But sometimes if you get lucky, you might be able to find one, or if you're studying some interesting varieties and that has interesting combinatorics, there's a good chance that when you work out some intersection numbers, you might have some nice combinatorial interpretations. So let me tell you what this x is that's suitable for this theorem. So for I ranging from 1 through d, let me write y sub I for a copy of P1 with E sub I many mark points, distinct mark points, no collision between them. Okay. So for each I have P1 marked with these many points. And now something one can note is that for let's say a committee, in other words, a subset where intersection with every EI is at most 1. Let's see. We have that y sub I take away the point labeled by S intersect EI. This is A1, assuming that this intersection is not empty. So for all I where the country is represented in the committee, and this intersection will be exactly one element. For each such I have P1 marked by those points. Let's also label those points by EI. So I take away that point. Yes?
In the construction of these yi's, are the ei's assumed to be disjoint as before?
Yes, so EIs will always be disjoint throughout the talk. And of course, you can start to ask like, can I make variations on that theme where they may not be disjoint? And I don't have any concrete answers, but it can lead you to something interesting. Okay, so for each committee, I have a bunch of these A1s. So what should I do now? Let Y be the product. So 1 to D of Y sub I. I mean, this is just P1 to the D. But each P1 has possibly a different number of mark points and so forth. And here are some rational maps that you can write down given a committee S. So I'll name them F sub S. So what do? First, I take this product and just project away, or only keep the I such that the intersection is not empty. Okay, so I have a bunch of products of P1s where S actually intersects E sub I. And then there is the rational map to projected space of dimension the cardinality of S. And what is this map? Well, inside here, I look at the product, or inside here, I claim that I have A to the cardinality of S. How? For each yi such that EI intersects S, I look at the corresponding mark points on that copy of P1, remove that, that's an A1. And I do that for each I appearing here. So I get this. And this has a natural closure, projective closure into this space. So that's the rational. So of course, it's not defined on the entirety of this. So this is only a rational map right now. So what do we need to do? Really get a variety. We set X to be the graph of all these rational. So I have Y pointing to product over all committees, possible committees you can make. Mark it where this is happening. A graph of, this is a rational map where you product together all these various different S, X of S.
How to think about rational maps.
Sorry?
How to think about rational maps.
How to think about rational maps. So rational maps by definition are maps that are not defined on the entire variety or entire space that you're looking at, but is defined on some open subset. And we're dealing with varieties here, so it's actually defined on a dense open subset. And by definition, that's what a rational map is. And I collect all of them together to get a map to this product. And by graph, I mean, I look at where this is defined, which is defined in some dense open subset, and then take closure. This, and by graph, I mean, look at the usual graph of this map on an open subset, and then take closure. And this.
Why do I want to take rational maps here?
Oh, good question. Why am I doing all these things? And it turns out this is the right X that we want. Yeah. Now, how would I know to do this? Good question. I mean, if we never saw this kind of moduli space of pointed rational curves with cyclic actions, it might be a bit hard to guess that this is the right thing to look at. I mean, the flavors are there. I have a bunch of P1s with distinct mark points, each labeled by these disjoint sets, E1 to E sub D. And I get a sort of natural projection map for each committee S or subset S, such that intersection with E sub i's are at most 1. Now, those maps are actually not defined on the whole products of P1s, but they're at least rational maps. So you can amend that by taking some sort of closure, and that's what the graph does for you. So depending on your exposure to algebraic geometry, you have either already learned or you'll eventually learn that this is a standard way to what people will say resolve the indeterminacy of this rational map by blowing up. But for now, you can just take it as some way of creating a nice variety X with all these maps, F sub S. And turns out that this is exactly the X we want. And these maps, well, you have maps F S1 dot dot F S. And so what do we need to prove now? We need to prove that with this X and with these maps, this intersection count is that panel count. So at that point, we can say, okay, we're done. You just count. Only it were that easy. And doing this intersection computation is really where the tropical methods come in, and it's quite helpful. So in the remaining time, I'll say a few words, as much as I can, about at least some pictures that go into proving or computing these numbers as intersection numbers of various hypersurfaces. Any questions? Okay. So what do we want to show now? So this theorem actually appears in our paper. Okay. So this is the real statement. And let me phrase it slightly differently in the language using cohomology. So let D sub S be the divisor class on that particular X that we have now defined, where it is the pullback of a hyperplane class from whatever projective space. Yes, in that case, dimension being cardinality of S. Okay. So a bunch of maps to P sub S. Take a general hyperplane. Look at its inverse image is some hypersurface. That hypersurface has some cohomological class, and we're calling that P of S. Then here's just the alternate way of phrasing that intersection number statement, which is when I cup product these divisor classes with appropriate powers given by alpha, this is equal to this panel count. So
What's a cup product?
Let me say, so this cup product occurs in the cohomology ring, which if you have seen and worked with what it is, great. If you have not, you can think of it as just in this language of take general hyperplanes and count the number in the intersection. Okay. But thinking of it cohomologically, it's quite helpful at times, especially if you have good control of what the cohomology of the variety that you're working with is. So maybe your complaint might be that what do I mean by cohomology if I'm over, say, like not over C? Whatever field that you were thinking of, let's say we're just over complex. I mean, you could work with Chow rings, but I think more people may have seen cohomology rings in the context of algebraic topology. Okay, so let's prove this. I mean, I will not fully prove it or succeed in fully proving it, but that's what we want to show now. Right? It's a cohomological statement. And for these kind of things is where these tropical intersection theory can come in quite handy. So let me define for you some polyhedral object that plays a key role. So here's a definition. For a subset, A and E, this is just notation. E sub A just denotes the sum of the standard basis vectors indexed inside A. This is an R to the E. Okay. And a definition, key object, is that of multi-permutahedral band. Of the data of the partition of E as before into, let's say, d-bin parts is a fan sigma that sits inside product of real spaces. So I take R to the E1 modulo the all one vector in R to the E1, in other words, E sub capital E1. Dot. So E R sub E. It's a fan in this space whose cones are, and I'm now into the board of last resort. So whose cones are the following. Cones correspond to chains of committees. Where if I have a chain, let's say S1, SK, bunch of committees. This corresponds, so this chain corresponds to, let's call the cone sigma, so sigma of this chain, let's call this chain C. And what is this? This is the non-negative span of the indicator vectors of these. Except that right now we have quotiented out in each of these coordinates, the all one vectors in respective set of coordinates. So let me put a bar to indicate where I'm in that quotient space. Okay. It's much easier to just draw a picture. So let me draw a picture. In small examples. Okay, so I'm really into the last words. I hope it works out. See. So here's one example. Let's say D equals 2. Let's say E1 is 1 bar, and E2 2 bar. Okay. And in this case, I claim that the fan looks something like this. So here is one bar, two bar. And here's 1, 2, 1 bar, 2, 1 bar, 2 bar, and 1, 2. And all the two dimensions you see. This one might be a little too small to give you an idea. Let's do just one bigger. So D still equals 2, but let's now say E1 is 1 bar, and 1, let's say, double bar. Okay, so 3 things. And E2 is 2 bar. Okay. So I have in the vertical line 2 and 2 bar in opposite directions. And let me I have 3, 1 bar, 1 bar in sort of a same plane. And for each of these pairs, I get a 2-dimensional cone. I haven't drawn in all the rays yet. There are a few more. So there are some missing rays, for instance. There should be a ray. 1, 2. 1 bar 2, and so forth. So let me not label all of them, but at least I'll mark them in. Although I feel like when you mark them in, it's like less clear what I drew. That's how it, so it's like 3 panels glued along this like single line. Okay. So it's some sort of polyhedral object. And let me tell you how this is helpful at all. And from here on, I will not really define or mention the results as precisely, but give you some idea what kind of works go into this. So you combine, for instance, works of RDL Clovens 6, and work of Tevelev 7. And I'll just say this fan is the tropicalization of this space X. Whatever that means. So tropical geometry gives you some way of producing a polyhedral object that remembers much about your variety, given the variety. And in this case, in some precise sense, when you tropicalize this variety X that we're concerned about, this guy, you exactly get these kind of multi-permutation bands. So that's fact 1. Then second thing to note, this can appeal to several different works. Let me just mention 2. Christian Procesi and Andreas Gross. So let me kind of summarize one upshot of what kind of applying some theorems from these works tells you, which is, let's say I have a tuple of real numbers, A sub s, indexed by s, where I have one real number for each committee. Okay. So I have a bunch of tuple, or I have a tuple of numbers, one number for each. And what this work tells you or gives you is that this gives you a divisor class, or if you like to think of it as some sort of a class homological class of a hypercircus, it gives you some sort of a divisor class, like these kind of D sub S's, or whatever these homological class that controls the intersection number. So it gives you a bunch of these. And as before, you can take the self-cut product of these, and let me write it more like a cut product. And this is a polynomial and so vector A is what I these two Cohomology numbers, one for each committee. Okay, so whatever it is, what it tells me is that when I go through this process, some sort of an intersection count varies in a polynomial way in these kind of parameters. So that's fact number one we can use. Fact number three uses a work by Anastasia, who's here. 23, I think. Okay. I don't know why I don't have this.
Yes.
Okay, all right. And let me give you one upshot. I'm kind of hiding a lot of subtleties underneath, but when this vector is really nice, or the technical term is cubical, whatever that really means. Let's consider the following complex. If I write here, can people see? All right. I'm starting to severely regret my choice of going to the board of last resort. So for each committee, I want to look at these kind of inequalities where the sum of the coordinates in the S's should be at most A sub S. So instead of really saying precisely what that means, let's say in this example, 1, 2, A sub 1, 2, let's say this was 3. Then I'm looking at a region where all points where dotting with this vector is at most 3. So in this region, let's say like A1 and A2 or both, I don't know, let's say 2. And the region I'm looking at looks something like that. So all the non-negative x's and respective kind of flaps where these A's are carving out some polyhedral complex by these linear inequalities. And the upshot of this is that when this is cubical, the volume of this not even well-defined set, but this polyhedral complex, the volume of this with the appropriate notion of volume is the self-intersection number, or is this couple. Okay. So the upshot is that for some nice choices of A, I can picture some polyhedral complex, and with the appropriate notion of volume, that gives me this number. And finally, the last step is that for A that are, it's a little bit unfortunate naming that we had to settle with for our paper, that are multi-matroids. So for some of you, maybe you just learned what matroids are. There are these things called also multi-matroids. And then there are these things called also polymatroids, and they're not the same. And the sort of the simultaneously generalization of multi-matroids and polymatroids are our multi-matroids. It's a little unfortunate, but that's what it is. So for A's, they are somewhat special. In other words, there's these kind of matroidy objects. The associated polyhedral complexes is, let me just say nice, really nice. And in fact, one way to really say it is that you can think of this as what's called a independence polytope or independence polytope of polymatroids glued together. So for these, we really understand these polyhedral pictures well for such special A's. And the volumes of these were computed in my work with Matt Larson, who's also here. And also 23. I don't know why I have these dates, but you got track. So what should be the plan? So we have explicit idea what kind of volumes these guys have. But this only happens when A's are whatever this R multimatroid is. Now, do those volumes actually equal these numbers? Well, if we know that's true when A is even nicer, cubical. So there are two conditions for A right now. Either it's cubical, where I can write some polyhedral, or I can consider some polyhedral complex, look at the volume, and it will compute exactly these cup product numbers. So for cubicals, these numbers come as volumes. For our multimatroids, we actually understand those volumes, but the set of A's that are R multimatroids and cubical are not the same. So you can't just automatically say, okay, we're pretty much done, because among these R multimatroids belong these D sub SIs. So our final goal was to compute these intersection of these like D sub SIs. And one thing one can notice after going all through this language is that for R multimatroids, these guys actually belong to this class. And their volumes of the associated polyhedral complex I understand completely well, and it actually equals to whatever that panel count that we wanted. But there's a problem to just finish at that point, because these R multimatroids may not be cubical, so that the volume actually computes for you these intersection numbers. But then polynomiality comes in to save your life. So there, thankfully, the set of R multimatroid is it's a full dimensional cone. Set of cubical divisors is also a full dimensional cone. And they in fact intersect on an open cone. And for both of them, the volume that you get or the degree numbers you get are polynomials. And if two polynomials agree on an open subset, there you go. So it's like a fact that I don't know, I never used since like learning about it. It's very useful, and that's how the proof goes. So lots of very different kind of techniques, from thinking about volumes of various convex, or really in this case polyhedral bodies, that plays a key essential role. And then there's tropical methods that allow you to kind of reduce to many of these polyhedral pictures, combine them together, and you finally get the kind of the panel count that you wanted. So I think during this week, I hope you learn at least many things that are of this nature. And I guess tomorrow you'll know actually what Lorentzian even means. So I guess tomorrow you'll finally understand what the theorem says. But with that, let me end here.
Other questions with this? Before we multi and poly everything,
Okay.
what's the statement? That's easier than.
Orally multi.
Just remove multi before there should be a analogous, is there analogous? Supposed to be simpler for more classical objects. Like before multi-permutahedral fan. Permutahedral fan. Just remove the word.
Yeah.
Everything.
So really this case is sort of really the non-multi-permutation case. So this case that I did with Matt. And so we're trying to reduce to the kind of non-multi case from the multi case. And the poly side, I think we tried to like prove it just with multi-matrix and like it wasn't kind of big enough to have this kind of good amount of intersection. So we like have to enlarge it. Or at least that's what I take away from the article. Failed attempts this one.
Asking this question for the audience.
Okay.
Let's say I don't understand multi anything and poly anything. Can I write it, but like supposedly there's the classical paper or papers that remove those words and like use these ideas.
Yeah.
If I strip away the multi and whatnot, what are those statements?
So without the multi, so statement in here is something of the sort where I bunch up subsets and I just want to count transversals. Or the count is either 1 or 0. 1 if there is a transversal, 0 otherwise. So when is it 1? And
Define transversal with
panels.
Yes.
Panels. So I guess that's the scenario where
Panel thing depends on you define with multi setting, right? Like can you do it without the multi setting? What does that mean?
so I guess that's the setting where all the E sub i's have one element.
Okay.
And something you might notice is that the multi-permutahedral fan as defined doesn't work then. So something funky is going on. I mean, if I mod out R to the one element modulo all one vector for each one of them, that's not a very interesting space. So I've got something a little bit different. And it's a little funky that you have to be a little more careful about like what the right combinatorial object is. But if you think in a more geometric way, especially in terms of the moduli space of pointed rational curves, it tells you a little more what to do. And the key word there is the stellahedral fan, which you may see or not see in your math journey either this week or going forward.
What about the stellahedral fan?
So really the right setting of or right fan in the non-multi case is the stellahedral fan instead of this multi-permutation.
So you mentioned it's like about module space of within rational curves with this not n action. So how does that not n come in? Is there?
So the scenario in the cyclic action case was where every subset had a same cardinality, like E1, E2, they all had the same cardinality. And so each of them now has the cyclic symmetry by that cardinality. So that's where the original symmetry was. Here we take at least the corresponding geometric object, relax combinatorics a little bit and see what we can get. And if you would like to say, you can say these divisors are actually certain psi classes on those moduli spaces and so forth. But at least we don't know how to prove these intersection numbers through that perspective of say psi classes.
Oh, in the theorem 2,
What is A arrow, the A arrow we're using here? Like how does alpha relate to this?
Oh, so A is just my notation for a vector in R to the committees.
Okay. And so in your theorem, are you plugging in a specific value for this vector?
So in trying to get the original theorem back, what I really need to know is what these numbers are for, say, as A varies, as like treat these A's as variables and try to see what these numbers are. And knowing all those numbers tell you what the intersection numbers are for any other situation. And there's a little bit of a, yeah, things hiding under the rug here, but that's it.
Okay, there's no more questions, and in fact, dinner is waiting for us at Simon's, so let's thank Chris again.